When we look up into a clear night sky, we see myriads of stars. And each of these stars is comparable in mass to the Sun. Between the stars, we know that there are vast oceans of empty space. We also know that around most stars there is probably a family of planets. But the mass of a star is far greater than the mass of a planet. For instance, the Sun is 1,000 times the mass of Jupiter, and the other planets of the solar system would easily fit within Jupiter. So almost all the mass of a star system is in the star itself. It might be reasonable to assume, therefore, that almost all the mass of the universe is in the form of stars. However, this does not appear to be the case. Astronomers now believe that most of the mass of the universe is in some form that does not emit light, and for this reason it is known as dark matter. Now, it's not particularly surprising that some of the matter in the universe doesn't emit light. We know that planets and the moon only reflect light from the Sun, they don't emit their own light. But what is surprising is that astronomers now believe quite firmly that 84% of the mass of the universe is in some form of dark matter that we really don't understand at all. What makes this all the more surprising is that physicists believe that we have a very good understanding of how the universe works. We have two incredible theories: the standard model of particle physics, which explains the structure of matter and the physics of the small scale. We have general relativity, which is our best theory of gravity, which explains the universe on the large scale. And both these theories have passed all the tests that they have been set. Recently, the Large Hadron Collider discovered the Higgs boson, which is the final particle of the standard model table of particles. And the standard model is being tested in very high precision experiments, but it passes every time. And similarly, general relativity is being tested in every way imaginable, and recently gravitational waves were discovered, and now black holes are established part of physics, and both these things were predictions of the theory. So we have theories that seem to be very accurate and work extremely well, yet we don't understand what such a large proportion of the mass of the universe is formed from. So given that these theories work so well, what evidence is there that dark matter actually exists? Well, the proposal that much of the matter of the universe might not be in the form of stars dates all the way back to the maverick astronomer Fritz Zwicky, who came to this conclusion when studying the Coma cluster of galaxies in 1933. Overwhelming evidence for dark matter has accumulated in the decades since Fritz Zwicky's original proposal. In the 1970s, Vera Rubin measured the rotation rate of edge-on spiral galaxies, and she showed that they are rotating so quickly that they would fly apart if they did not contain much more mass than we can see in the form of stars. So the mass of the galaxy is largely in the form of dark matter. And there are other independent methods of measuring the mass of a galaxy. One of these is gravitational lensing. Gravitational lensing was originally a prediction of general relativity, which suggests that the mass of a galaxy will bend light around the galaxy. So we can see arcs in this image of galaxies that are beyond the main galaxy in the image. The light from these distant galaxies is bent around, and this can be used to determine the total mass of the galaxy that is doing the gravitational lensing. And again, we find that the mass must be much greater than we can see in the form of stars. A completely separate line of evidence for dark matter comes from the analysis of the cosmic microwave background. And this is radiation that was emitted by matter in the very early years of the universe. So it dates back to just 380,000 years after the Big Bang. and it would originally have been in the visible region of the spectrum, but the expansion of the universe in the 13.8 billion years since now means that we detect it as microwaves, and in fact it has the spectrum that would correspond to the radiation emitted by matter at just 2.7 degrees above absolute zero. But there are tiny variations in this temperature, and if this is mapped out across the sky, it gives evidence for the clumpiness of the matter in the very early universe, and each of the clumps will go on to become a supercluster of galaxies. Now, the analysis of these variations allows physicists and astronomers to deduce information about the matter content of the universe. And this analysis shows that 84% of the matter in the universe is dark matter. So if all this dark matter is out there, what is it? What form does it take? Well, there are a number of possibilities. One is that it's in the form of dark gas clouds. We know that there are clouds of gas throughout the galaxy that have not yet collapsed to form stars, and that these gas clouds are very massive. So could this be the answer to dark matter? Well, in fact, we know that it can't be, because the models for the very early universe and the elements such as helium and lithium and deuterium that were produced in the very early universe match observations very well. And if there was significantly more ordinary matter in the universe, this match would no longer work. So we know that there can't simply be lots more ordinary matter. Another possibility might be black holes. We know black holes are essentially black. Could they have been formed in such vast quantities in the early universe that they might explain what dark matter is? Well, although we can't see black holes, there are ways to determine that their presence. And one of these is known as Gravitational Microlensing. And this is when a star passes behind an invisible black hole, but its light is enhanced by the gravitational lensing around the black hole. So if we look into the halo of the galaxy, we might expect to see sudden brightenings of a star, and this is an indication of the presence of black holes. These events have been seen, but not in the quantities that would explain the existence of dark matter. And similar recent observations have looked at supernovae in distant galaxies, and again, if black holes were present in great quantities, these microlensing events would brighten the supernovae, but no such event has ever been seen. So it seems pretty clear that black holes can't explain dark matter. Another possibility is neutrinos. Stars and supernovae produce vast quantities of neutrinos, and this universe is swarming with them. They pass through our bodies all the time, and they interact so weakly with matter that we know that virtually all the neutrinos ever produced are still out there. So could these vast quantities of neutrinos explain dark matter? Well, we now know that the mass of a neutrino is about a millionth, at the most, a millionth of the mass of an electron. And so even with the vast quantities of neutrinos, the total mass in the form of neutrinos would only explain 1 or 2% of dark matter. None of these fairly conventional solutions appears to work. So this brings us back to our two great theories, general relativity and the Standard Model. It suggests that at least one of these theories needs to be amended. Now, some people believe that we need a new theory of gravity to replace general relativity, but most physicists don't go along with this view for a number of reasons. One is that general relativity is a very beautiful theory, perhaps the most beautiful theory of physics ever invented, and so it's not easy to amend it to fit observational anomalies. Secondly, general relativity passes all its other tests with flying colours, so it seems a bit premature to ditch the theory. But a more convincing line of evidence probably comes from the gravitational lensing studies, which show that dark matter is situated in different regions of space to ordinary matter that we can see. So it doesn't seem to be possible to solve the dark matter problem with a new theory of gravity. So we should take another look at the standard model. And this is the solution favoured by most physicists. The expectations are that there must have been a new fundamental particle that interacts extremely weakly with ordinary matter, perhaps more weakly than neutrinos, and that this particle was produced in vast quantities in the very early universe, and because it's completely stable, it's still there, and this is what dark matter is. Now, there are two ways that we might prove such a hypothesis. One is by trying to create new copies of the particle in a machine such as the Large Hadron Collider, and the second possibility is with a cosmic ray detector, so we might detect these particles in cosmic rays. Theorists have produced many models that go beyond the standard model and predict the existence of particles that might explain what dark matter is. And these particles go by names such as axions and neutralinos. And the Large Hadron Collider, one of its main goals is to find the particle that would explain what dark matter is. And one of the theories that's been pursued most heavily by the Large Hadron Collider is supersymmetry. And this is a symmetry, a hypothetical symmetry between matter particles such as electrons and quarks, and the particles that are exchanged to produce forces such as photons and gluons. And supersymmetry suggests that for every matter particle there should be a force exchange particle and vice versa. But the currently known particles can't be matched up in this way. So if supersymmetry is correct, then there are many more particles awaiting discovery by the Large Hadron Collider. And the lightest of these particles would be expected to be completely stable, and it would have been produced in vast quantities in the early universe, and because it's stable it would still be out there and could explain what dark matter is. This particle is usually referred to as the neutralino. Now, unfortunately, although the Large Hadron Collider has been searching for supersymmetry for a number of years, it has found absolutely no evidence so far at all. So there is no trace of any of these new particles. That brings us to another method that we might use to find the origin of dark matter: cosmic ray detectors. Some of these detectors are dedicated to the search for dark matter particles, and these include a detector at the University of Washington in the United States that is designed to detect axion particles if they exist. Another such detector is the Xenon 1T detector in the Gran Sasso mine in Italy. There are a number of other detectors that have been designed to detect neutrinos, but they are also on the lookout for dark matter particles as well. And these include the ICECUBE detector that has recently been built in the Antarctic. An ICECUBE is searching for any particle interactions in a cubic kilometre of Antarctic ice. The question of dark matter really is one of the biggest mysteries of the cosmos. But it's one that we expect to solve within the next 10 or 20 years at most. Huge efforts are being placed into the search for the origin of dark matter. And if a solution isn't found in this sort of time period, then physicists will have to rethink their theories. We'll be taking another look at astronomy and stars in a series of videos in the near future, so please do join us very soon.